Hey everybody, chapter 4, lecture number 3. We skipped chapter 1. We got some review, lots of review a little bit already, which is good. I'm a big believer in the early stages of learning that repetition aids comprehension. In the early stages of learning, repetition aids comprehension. Now, I think as you become intermediate and or experts, the repetition is no longer necessary quite so much, but especially in the early stages, that's good stuff. So, we're going to review some data types and introduce a lot of new stuff here. So there is some review, but there's a lot of new stuff. And so when you look at some of these bullets, like, yeah, we've done this, we've done this. We need to dive a little deeper into like how math works in C#. And so there's definitely some things that we haven't covered. And like in your math class, it works one way, but when you do some math in your code, it might actually work a little bit different. And so there's some built-in utilities for us to use. Like, you know, fortunately, we don't have to what's the expression? You don't have to rebuild the wheel. The wheel's already built. We can use some stuff that's already been built for us and solve some common math problems using the built-in tools. Generating a random number, got a fun little YouTube video about can computers really be random? It's kind of a philosophical question because as coders, we're telling a computer what to do. And so anytime you're telling a computer what to do, can it be random? And there's some really unique ways that computers can seemingly be very random. Fun little story of about randomness. Going back 20 years, there was a game show called I don't know what it was called, but they would always go no whammy, no whammy, no whammy, and then they'd hit the buzzer. You know what I'm talking about? Yeah. Something your luck, trust your luck, yeah. Bust your luck, something. Push your luck. So, and so Push Your Luck had this box that was jumping around in a seemingly random order, and one of the television viewers of this show, this probably isn't so random. Let me study this pattern, and he studied the pattern of the seemingly randomness that the computer was generating, and he found out that there was a pattern, and he ended up winning millions of dollars because he got on the game show, figured out how to not have a whammy, and would always hit like a $5,000 prize. And
it's like card counting.
It's like card counting, yeah. It's a system, right? There's a system to generate random numbers. If you understand the system, then can you fake it? There's some really interesting ways that random numbers can be generated in software today that, yeah, you could never predict it. But anyways. Converting data types is another thing we need to learn more about. Scope is a mouthwash, right? So scope is a mouthwash, but scope is also a programming term that refers to when a variable can be used. And so we've made variables and we've used variables, but variables occupy RAM, right? So if a variable's no longer, if you don't need it, if you don't need a variable to be used anymore, you kind of want to give that RAM back to the operating system so that the operating system can give it to another application if it needs to, right? So your application uses RAM, but it needs to also give RAM back. And so when a variable is no longer needed, you need to discard it. It needs to go out of scope. Okay, and so scope is this concept of like, hey, a variable is no longer needed, therefore it's out. You need to have it go out of scope so that RAM can be reallocated to other applications. And if you're good at this, right, then your applications run very efficiently. We've all probably used computers for a long period of time without rebooting them. And what happens if you don't reboot your computer over a long period of time, these applications take RAM and they don't return it. And that's, ultimately it's called a memory leak. And when applications don't return the RAM back to the operating system, your computer slows down, right? That's a result of that. So we'll get into this concept of enumeration. Some of this stuff, again, we're going to break this into multiple parts. And so we're not going to probably get to these later objectives today. Again, talking about casting, operator order of precedence, different types of variables, value versus reference types. Okay. This chart on slide 5 and 6, we've actually, you saw that chart in that Prezi. So this is the chart, but that Prezi simplified this chart. Okay, that Prezi had less data types in it. You can actually see there's more data types on this chart. The Prezi covered the common data types. Some of these in here, like U-short, is a short that uses 2 bytes, just like a short does, but it's unsigned, which, if you remember what unsigned means it can only be positive. Okay, so it's the same amount of storage, but instead of negative 32,000 to positive 32,000, as far as the range of values, it's all 65,000 numbers are positive. Okay, so we got, again, bytes, signed bytes, shorts, unsigned shorts, ints, unsigned ints. Again, that gives you an int is basically negative 2 billion to positive 2 billion, whereas an unsigned int is all positive 4 billion. Then we got longs, unsigned longs, floats, doubles. Nothing really too different there. This one's different. Decimal. Now, if you read the textbook, they say, look, decimals are really the data type that you should use for storing monetary values, because these are actually pretty good at high precision of decimal points, like lots of precision when it comes to decimal points. And so, kind of looking at the float, 8 bytes, a double is 4 bytes, a double is 8 bytes, a decimal is 16 bytes. So to be most precise with money, basically they recommend decimal. All right, let's open up some code. I just want to show you something kind of interesting. Again, just as a refresher, we're going to start chapter 4 by creating chapter 4 solution. Yeah, what's up, Anil?
So why did they want you to use a decimal for monetary value if you're only going into 2 decimals?
Good question. So, you ever seen the Office Space?
The movie?
Yeah. Do you remember how in Office Space, do you remember their big scheme to make money? Who wants to remind me the big scheme in Office Space?
So the big scheme in Office Space was that they were going to take fractions of a penny and they were going to deposit it in their account. So like the fractions that happened like past 1 penny, that's what they were taking basically.
They were taking fractions of a penny. So yes, in the physical space that we occupy, monetary value only has 2 decimal places. However, when you start doing division of money, you're often left with like repeating 3s, right? And so you take this number divided by that number, and that's supposed to be the change that you get, but you got to round up to like 33 cents or 34 cents. You got to round down, you got to round up. Okay, and so in jokingly in Office Space, they say, okay, we're going to take that repeating 3, we're going to take all these repeating 3s, and we're going to add them together, and we're going to get pennies. In millions of transactions, you get dollars and thousands of dollars. Okay, so in math, you're often left with these long decimal places as a result of the math that you're doing. And so to account for the most accuracy, ultimately, yes, you're going to have to round up or round down, and banks do that. But does that answer your question?
It does. I wasn't thinking about using fractions of
division. Yeah, fractions, exactly.
Fractions of like pennies and stuff
Exactly.
That was kind of a minor plot point in Superman 3.
Was it?
Yeah.
Superman 3?
Yeah. Yeah, because like Richard Pryor was like this hacker, and that's kind of his scheme he ran was to get those.
Richard Pryor was in Superman 3?
Yeah, the movie wasn't.
What year was that?
80 something.
80s?
Yeah.
I mean, I remember watching those in
83.
yeah, a long time ago.
That movie wasn't very good.
I went with Office Space because it's still kind of a cult classic.
They actually reference that Superman movie.
Yeah,
in
that's what I'm
Office
saying.
Space.
That's kind of
Really?
Yeah, they did.
Learn something new. That's fun.
I love that movie.
I'm just gonna do a console app, not like it matters. Remember here, what do we select here?
The chapter.
Not the chapter.
The lab.
The lab folder. We select the lab folder. So this is the parent folder. The solution name is the lab. Now what is the lab? This is chapter 4. So CHO4. That's the proper way to do it. Still some people are kind of doing it incorrect, but it just comes with practice. Visual Studio Update is now available. Let's update on close. That's great. Okay. All right. Everyone's with me on the double? Why then when I do this? Float number 2. Why does that not work?
Because you need to put an F at the end of 0.3.
You're correct. What does that F do?
It converts both sides to floats because
Yeah.
on the right side is a string, if I'm not mistaken.
You're barking up the right tree. All right. What happens when the C# compiler looks at this is you see a float on the left and you see what's known as a floating point number, which just means it's a decimal. You see a decimal on the right. So when the compiler looks at this 0.03, it says, well, what's the data type? It has to pick a data type. The compiler says, okay, well, it could be a float, it could be a double, it could be a decimal. It's got to pick one of the three. So the default, by the way, okay, 0.03 is known as a literal value. So there's a term, a literal value. A literal value is a coded value into the program. So you assign it, you literally code 0.03 into the program. Well, what's the opposite of a literal value? The opposite of a literal value is getting user input. Instead of you assigning a literal value to that variable, you would ask the user to enter a number. Okay, so keep that word in mind, a literal value. When you have a literal value that's coded into the program, the C# compiler has to say, I got to give that a type. What type does it give it by default? By default, it gives it a double. That's why you don't need any special letters after a double. You got a double on the left, a double on the right, all is good. Now, on this one, you got a float on the left and a double on the right. Which one, a float or a double, has more precision?
Double.
A double. Why does a double have more precision? Because there's more bytes of storage. So the rule of thumb is a double has 15 points of precision, roughly. A float has roughly 7 significant digits of precision. Significant digits meaning before and after the decimal point. So what the compiler sees here, and this isn't important, this is theory out of the book, right? This is programming common theory. The compiler sees you've got 15 points of precision on the right, and you've got 7 points of precision on the left. You're trying to take a big storage unit and cram it into a smaller storage unit. What am I talking about storage unit? Well, go back to your slides and you would see that you got 4 bytes here, you got 8 bytes here. You're trying to take 8 bytes of storage and potentially save it into 4 bytes of storage. That's not going to work. That could potentially cause problems. Okay? When you've got more storage and now you're trying to save that information into a smaller container. Okay? So the name of this, right? The reason this is a problem is this is called a narrowing conversion. Everyone remember? Everyone, write that down, whatever. Take a note. Narrowing conversion. When you're trying to take a wider storage unit and convert it down into a more narrow storage unit. So here's the rule of thumb. Narrowing conversions basically could cause data loss. Narrowing conversions could potentially cause data loss. If you've got this 15 digits you got this number that's 15 digits of precision, and you need all 15 digits, and you save it in 7 digits of precision, you see you could lose data there. So narrowing conversions could cause data loss. Data loss could be a problem. Data loss could be a big problem. You don't want to lose data. So anytime there's a narrowing conversion potential, they force you to do a conversion. Okay, look, we're going to let you store this double into a float, but you're going to have to code that. You're going to have to say, I know what I'm doing. I want to take this double and I want to cram it down into a float. And the way to do that is by converting it. You call it converting it or casting it. It's often called casting. And there's different ways to convert. One way to convert this is by just putting an F. So by putting that F there, you're converting a double, which it is by default. It's a double by default. And you're performing a narrowing conversion. You're saying, you know what, this 0.03, I know that there could be data loss, but there's no data loss. It's just 0.03. I know what I'm doing. Let's go ahead and make sure that it's a float on the left, it's a float on the right. So because it's a narrowing conversion, the conversion has to be coded by you. That's called an explicit cast. EX. Okay? Explicit just means you code it. Okay. Not all conversions are explicit. There's another kind of cast that happens automatically. If narrowing conversions have to be explicitly cast, there's the opposite is called an implicit cast. Implicit cast just means it happens automatically because it's a widening conversion. Widening conversions, like I'll give you an example of a widening conversion. Well, 1 is a whole number, so what you actually have on the right is an integer. An integer is just a whole number, but you're going to store that into a double. A double is a wider, because it can hold decimal points. You're not going to lose any data there. You're just going to add decimals, and the decimals are going to be 0, 0, 0, 0, 0. So because there's no potential for data loss, there's actually a cast that's happening here automatically for you, and you really don't got to worry about it. It's just, believe it or not, there's a conversion that's happening behind the scenes here for you. Okay? So rules of thumb, pretty simple. The explanation, a little bit more detailed. Okay? Rules of thumb, narrowing conversions, anytime there might be data loss, you're probably going to have to perform a cast. anytime that there's really no worry about data loss and it's a widening conversion, there's probably an automatic cast that's happening for you. Okay, so this might be an implicit cast. Explicit means you code it, implicit means automatic. Okay. Well, decimals kind of work like floats. And that they don't work automatically. Now, the way to cast that is by putting the letter M. So it just, my rules of thumb about widening conversions and narrowing conversions, it's kind of interesting because when you think of a decimal, decimals have more storage. So what we have here is a decimal on the left and we've got a double on the right, and yet they're still making you cast it even though it's a widening conversion. So I can't really explain that one, but they just, I don't know, they still make you do it. The way to do it is actually with the letter M. The main premise is you're just saying, hey, it's a decimal on the left, it's a decimal on the right. There are other ways to do explicit casts, not just putting a letter. I'll give you another way of doing an explicit cast. You could just do something like this. In a lot of cases, now that doesn't work here, of course, as I say it would work. So I believe it will work on the float though. So this is another way of doing an explicit cast. Instead of just putting the letter F in front of it, you put the data type in parentheses before it. And it does the same thing, it converts. It converts the data types. Okay. Another way to do an explicit cast is, you guys have seen, you've done this one, convert to double. Convert to, someone pointed out to me, there is no float. And so if you kind of scroll through the options, we're looking at to single is going to be your float. So convert to single. And so there's more than one way to do explicit casting. Okay, you just put the letter after it, you put the data type in parentheses, you've got these whole array of converts. Okay, this is called the convert class. Okay, here's one more, as if you need another. You probably don't need another, but just to throw this out there, because the book will show it to you. You could also say each one has float. There's a class float.parse. Which you'll often see this, which is another tool. Now float.parse will take a string value. So I believe you got to put that in a string. So the data type .parse takes a string and converts it into that. So all these are just different ways to do explicit casting. Let's take some questions.
Okay, so I guess I have two questions. So the first one is, what happens if you try to like add, multiply, or divide integer and a float, or like a float and a double? Do you
Great.
have to do some conversion?
Great question. What happens when you multiply 5 times 0.03? The result is going to be the wider.
Okay.
The result is the wider, which is the one with the decimal. So so if I say, and it just kind of makes sense, right? So it would be double result equals 0.03 times 5. What's going to happen is on the left we have a double. On the right we have a double times an int. So the compiler looks at that multiplication and says, okay, I need to choose the wider of the two, which is double. And therefore the result of that math is a double. So you got a double on the left, double on the right. Good question. Yes?
So if you use like a data type that wasn't a double, that couldn't fit like a decimal, it would get.
Yeah, this is probably gonna, yeah.
Okay.
It's like, hey, you got an int on the left, you got a double on the right, data types don't match. Data types have to match left and right. And sometimes conversions happen automatically, especially in math. Yeah.
Okay, so with the parse, I know we use that in JavaScript.
Yes.
Is that something where, like, if you had user input, it would be inputted as a string, and then you'd have to parse it into?
Yeah, and so a lot of console.writeLine, enter a number. You know, this is another way of doing this. You could say float number 5 equals, and some people even started doing this. Float.parse, console.writeLine, readline. So it takes the readline string, parses it into a float, stores it in a float. And so here you could use float.parse, or you could use convert.toSingle. And those are two different ways of doing the same thing. But yeah. All good stuff. And camel notation, meaningful names. You know, everyone was doing this on their test yesterday. What's the other one? Camel notation is what we use for our variables, but what was the other convention? Pascal notation, right? Camel notation starts with a lowercase first word, and then every new word is capitalized after that. Pascal starts with a capital letter, and every new word is capitalized. So that's again, those are naming conventions for our identifiers. Okay, variables need identifiers, but there are other things like methods. Methods are also identifiers. You get to identify your methods. And methods might follow Pascal notation, whereas variables follow camel notation. In fact, take a look right here. Readline is a method. What notation does it follow? It follows Pascal, right? How do I know that's a method? Because it's got parentheses on it. Scientific notation, you know, in your math class, they put the caret, like 7 to the 8th power would be 7 caret 8 or whatever. In the computing world, it's the same thing. It's E notation. So, you know, this is this number to the 9th power. It's just E notation. That's what they call that, but it's the same. It works the same way as your math class's scientific notation. So what does that mean? It means you move the decimal point 9 places to the right, something like that. Just a reminder: chars go in single quotes, strings go in double quotes. Sometimes you need to do some casting to, right? One common mistake is when a new coder wants to store like a number 1000, like in an int. So int number 6 equals, they do something like that, right? So you actually don't, in your source code, what's it called when you code a number into your source code? Literal. It's called a literal. When you code in a literal value, you do not put like commas, but you do put decimals. Okay, so there's no commas in your literal values. So that's a common mistake.
The book said you can do underscores.
And they demonstrate that.
Oh, okay.
Yeah, they demonstrate that. That's somewhat new. I think that's a newer feature of C#.
8.0 and newer, yeah.
Yeah, because I don't recall that prior to this textbook. Good stuff. Again, even just looking at the syntax of a variable, you start with the data type first, then the identifier, and then the assignment operator, which is the equal sign, and then the value that you're going to put into it. So this is known as declaration and initialization. Declaration is giving it a name and a data type. Initialization is giving it a value for the first time. So you initialize your variables, init. One optional thing is making something constant, meaning it cannot change. Remember, and I demonstrated this, if you make something constant, you have to declare and initialize it on the same line. You can't even break them up into two lines anymore. So if you declare something as constant, you have to initialize your variable on the same line. And it is common with constants to do all caps. Okay, so go ahead and mark the convention for constants is all caps and underscores in between words. That's, again, conventions in the class versus conventions in the book. We mostly follow the same conventions. Obviously not all the time. It is, in my observation, constants are more typically all caps. Okay, so I keep that convention in my coding practices. All right, let's go ahead. We've been going for 30 minutes. Let's take 10 minutes, take a quick 10-minute break. I'll pause the recording. And we're back, and we're going to resume. Remember that PEMDAS? Who remembers what that was?
We're about to reorder. Excuse my dear end, Samuel.
Yep. It still applies here, right? You got to remember your order of operations. Some of you were reminded of that during the lab. Like you gotta, sometimes I jokingly say you gotta throw parentheses at it until you get the answer you want. Just keep throwing parentheses at it until you get the answer you want. Parentheses, exponents, multiplication, division, addition, subtraction. Some unique features of C#. Like, check this out. This might surprise you. Not 10 divided by 2, excuse me. Let's do 10 divided by 3. Where'd the decimal places go? We got a double on the left. We got a whole number divided by a whole number on the right.
You got format, don't you?
How would you format it?
I think it's an N.
Add a decimal.
So maybe that? No? So what's happening here? Let's explain it first, and then we could talk about how to fix it. So let's understand the problem first. The problem is 10 divided by 3 is going to be 3 1/3, right? 3.33333. So when I would look at this, I would expect the output to say 3.333 repeating. And instead I just get the number 3. I've lost data. That's not good, right? What's actually happening here is you're taking a whole number divided by a whole number. The compiler results in a whole number. Int divided by int, result is int. This is actually called integer division. Integer division results in a whole number. And so that's just the way it works. You would expect something different in your math class, but in the C# world, you take a whole number divided by a whole number, you result in a whole number. Now, the easy fix that I know is make one of those whole numbers, just throw a decimal on it. Now you've got a whole number, an integer divided by a double, the result will be a double, and then it'll store it in a double. So the question is, do you want, there was a problem several of you that were doing, which was like saying int number of eggs is 13. And you were trying to figure out how many dozens there were, right? So you could say int dozens equals number of eggs divided by 12. You're not really cared about the remainder. You just want to know how many dozens there are. There's 1 dozen. In the case of like 25, if there were 25 eggs, well, there's 2 dozens. You don't really care about the remainder. You just want to know how many dozens there are. How many dozens of eggs. And so here we're doing integer division on purpose because we don't really care about the decimal point, right? So integer division can be used to solve problems, right? It's not necessarily a bad thing. You just got to know how it works. Okay, because when I was first thinking, I was like, oh, integer division, that's a bad thing. Well, no, not if you understand it. You think, oh, you're losing decimal places. That's bad. Well, you only lose decimal places if you choose to. So that's integer division. Another fun thing is modulus. Int remainder. Modulus is just a remainder. Before you learned decimal points, you learned remainders. Like 15 divided by 2 is 7 with the remainder of 1. Right? If we do 19 divided by 6, that's 3 remainder of 1. If you do 20 divided by 6, that's 3 remainder of 2. Like, remember, we all learned remainders before we learned decimal points. So what is modulus? Modulus is just the remainder. Like if I do 20 modulus 6, console right line remainder, what's my hotkey? Control F5. I just got the remainder here. So remember remainder, which is different than a decimal point, right? How many left over? So this can also be used to solve problems. I believe some of you were doing yeah. So like, what was the amount of currency you were trying to break up? Like if you had $150, right? Then you would say int number of 20s equals 150 divided by 20. Int remaining money equals 150 mod 20. So you would get integer division here to get your 7, and this would be remainder of 10 with $10 left over. So you get 7 $20 bills with $10 left over. Right? So again, integer division and modulus can be used to solve problems if you understand how they work. Other than that, I will say that there are test questions, like no shortage of test questions about doing mathematical operations in C#. My advice around those is to plug them into Visual Studio, see how they work, right? That could be a good learning experience for you. We covered prefix and postfix, all that fun stuff yesterday. We talked about how this would work yesterday. Lots of book examples on, shorthand operators. We've talked about that before. Basically, same order of operations that you're used to. If you need to make sure something happens outside of a normal order of operations, you put parentheses around it. So here's some implicit casting. We talked about implicit casting. Again, implicit meaning automatic. So bytes can be converted up to short, can be converted up to ints, longs to decimals. So again, these are all widening conversions. Ints can be automatically converted to doubles, shorts into floats, and then into doubles. Chars can be converted into ints. That's an interesting one. Chars can be converted into ints. And so, again, widening conversions are the general rule of thumb. Implicit conversions happen automatically. A lot of times you don't even realize they're happening. They just happen. And that's nice. Again, another way to do an explicit cast is by putting the data type in front of the number. So like here, we're going to basically chop off the 70.75, and it's going to be, the grade is going to be 93. Someone in the class did that the other day. They're like, well, in your grade book, you just get a 93. You don't get a 93.75. You just get a solid grade. Okay, and the question always is, do you round up or round down? If you round down, well, you could just, it's called truncating. This truncates the 0.75, it chops it off. This takes the decimal value of 65, converts it into a char, and if you look at an ASCII chart, decimal 65 is equivalent to the letter A. Remember, we kind of went through that in a prior lecture as well. Okay. As we're getting into math, so as we see, okay, order of operations and how these operators work, it then does make sense to kind of look at what are some of the built-in utilities that we can use in C# that can help us do some math. And so there is a class called Math. And just like if I'm looking here, let's break down a counsel right line. Let's take a look at this line. Counsel is a class. And so there's a built-in class in C# that has in it, inside of the counsel class, you could actually find this method called WriteLine. And so keep in mind, classes are blueprints for objects. And sometimes with classes, you build objects. Other classes are called utility classes. Utility classes just have a bunch of built-in methods that you can use. So counsel is a utility class that has a method that just built into it that you can use called WriteLine. And inside of the WriteLine method, there is a coded value, to be specific, that's called a string literal. Right? You're coding in a string literal here. It's a literal value. You're coding it into the program. and you're taking that string literal and giving it to the right line method. It's called passing it. You're passing it to the right line method. Well, math is another utility class, much like counsel. And if you explore this, there's a whole bunch. Remember those the methods are on this cube. Constants are in this square. So basically we're looking at a bunch of constants or methods. Like let's look at the constants. I got Math.Pow. Who's the world record holder for who's memorized the most of Math.Pow? Like 99 digits of pi. 3.14286, right? Oh, impressive. What is it?
3.14159 is as far as I can.
Ah, that's good. That's good. More than me. Math.Pow is used in enough equations, they just give it to you, right? So all we're doing here is we're sending Math.Pow to the right line statement and just showing you basically 3.141592653589793 on March 14th, on 3/14, there's always people who compete to see who can memorize the most Math.Pow. Okay, that is a constant, or just a piece of data that doesn't change. But when the methods, look, Math.Absolute. A cosine of an angle, a cos. All right, for all of you that have been through that's trigonometry, right? Cosine and sine and tangent and logs and all that fun stuff. The sine. So the ceiling returns the smallest int value that is greater than math.ceiling of a decimal, 0.23. So math.ceiling rounds up to 1. Right? So all these methods are built into this utility class. The utility class is called math, that is there to solve a bunch of problems. Now, these are common ones. Math.Round. And if you look at Math.Round, you could see it accepts a decimal. So like in this class, let's see, you get a 93.4. Okay, that rounds to a 93. If we go 93.5, that rounds up to a 94. So you just got to see how these work. Let's see if a 93.49. So just out of the box, that 9 does not round up. It looks like it rounds to the 10th. It rounds to the 10th place, right? But what if you want to specify a different number of precisions, right? So maybe the second argument here, comma, how many decimals? All right, now let's see what it does. It would do, let's just do 495. Now there we go. So that gets you to round up after the second decimal. Yep.
So what exactly is that 2 doing? That I don't think we've learned that before.
Well, it tells you after the second decimal place to round up basically here.
So if it was a 1, it would be looking at the 4.
Yeah, I believe it's a 1. So basically, yeah, how many precision points?
Okay.
And okay. So that's what the precision does on a decimal. You can round at different, the tenths place or the hundredths place or the thousandths place. Basically, where do you want to round your number to? Math.Pow is, let's take 2 to the third power, right? So if I want to take 2 to the third power, I would use Math.Pow. Math.Pow. I would take a number to a power. So let's take 3. 3 to the second power. Let's just do that, right? 3 to the second power is 3 times 3, which is 9. Let's take 3 to the third power. 27. Right? So on and so forth. So 3 times 3 times 3, right?
So are those integers that...
It does, it takes, if you look at Math.Pow, double. So we could take 3.2 to the second power. And get 3.2 times 3.2, whatever.
So it automatically creates a data type for it. You don't have to convert Math.Pow.
Yeah, exactly. So if we look at that, what's interesting here, if you look at the signature of Math.Pow, it tells you a couple things. It says it accepts 2 doubles. So that's what you put inside of Math.Pow. And you talk about, well, it picks the data type. The data type that it returns is double. So you can actually look at that word right there and know that Math.Pow is going to give you back a double. Regardless of what you put into it, it's going to give you back a double. So this first line right here is called the method signature for Math.Pow. Math.Sqrt, right? Well, again, we're talking about the math class. It's a utility class, Math.Sqrt. And again, we'll do the square root of 25. Of course, 5 times 5 is 25, so the square root of 25 is 5. Again, just so you don't have to solve it, you just use the utility class. And finally, on the slide, we got min and max methods. So let's do Math.Min. Returns the smaller of 2 unsigned ints. So this is a method to basically say, hey, I got 2 numbers, I want to know which one's smaller. Hey, I got 2 students, one's 15, one's 30, which one's smaller? Who's younger? All right, so 1 comma 3, let's just even put our data backwards. We should still get 1. Sometimes it takes a while, but there you go. Right, so now, interestingly enough, this min has these are all called overloads. So you can give it different data types. Look, you can give it bytes, you can give it decimals, you can give it doubles. So as I'm hitting these arrows, you can see this min method works with different inputs, not just bytes. Yep.
Do they have to be like whole integers, or could you do like, say instead of 3 and 1, you wanted to put like 1 plus 2, comma 1 plus 0?
You could do that, yeah. So 3, you could do 1 plus 1, and that would know that that's 2.
Okay.
Yeah. Let's see if we do that. How about that? There you go. So, a class, it is true, a class is a blueprint of an object, but sometimes classes are just utility classes and they provide some functionality for us. And the math class is one of those classes, and those are some of the common methods that we've covered. Right? Round to a whole number, round to 2 decimal places. Area of a circle, right? Area of a circle is the radius, Math.Pi times radius square, right? The area of a circle, Math.Pi times radius square. Square root. Hey, I've got 2 numbers. Which yearly sales was more, this year or last year? So you could pass in variables here. Which was our slowest quarter, this quarter or last quarter? Good little demonstrations there. Bunch of examples on how to round to 1 decimal place, 2 decimal places. Kind of demonstrated that. Here, it's like you're providing 2 arguments. These are called 2 arguments. You're separating them by commas. What's the number to round into how many precision points? Number to round and how many precision? This one's 3 arguments. And you can kind of look at that third one. Again, if you do a Math.Round, you can, let's do Math.Round. And you can kind of scroll through the different signatures and you get a midpoint rounding mode. It's kind of really getting into the nitty-gritty on how rounding can be done. So let's provide a decimal, 12 point, what have you. Let's say to 2 decimal points, comma. Says rounds a decimal value to a specified number of fractional digits using the specified. Okay, I don't even know. I'm sure the book will explain a little bit more detail, but I've never used that.
It doesn't round up, it just rounds, it doesn't even round, it just kind of like takes off the number.
Okay.
Just chops it off.
Thank you. Thank you for that. Just chops off the number. So if we do as the midpoint rounding dot, and these are the different away from 0. The strategy of rounding to the nearest number, and when the number is halfway between 2 others, rounded towards the nearest number that's away from 0.
Oh, never mind, that's wrong.
The smaller, basically sounds like the smaller.
Well, you can do 2, 0, and then away from 0. Or 2,
Yeah.
and then,
Yeah.
depending on-
If I promise you, if you like get into like financials and banking software, this kind of stuff really matters. So that's when you really dive deep into this kind of stuff.
That's cool.
Yes. Okay. I think we're going to find a good stopping point. I'm going to do one more utility class, and then we're going to stop. Open up the labs. The random class, let's just go through the random class. We're going to start with a fun YouTube video. I'll throw this on the recording because why not?
Computers aren't very good at picking random numbers. Every part of a computer is designed to be predictable and follow logical patterns. You put the same numbers in, you're going to get the same numbers out, which is a problem because all modern encryption, including that padlock up in your browser that tells you that you're safe, all of that relies on big, properly random numbers. If you can somehow predict those numbers, you can start breaking those locks, which is why I'm here at the headquarters of Cloudflare in San Francisco.
Cloudflare is a service that protects websites and web services and sort of sits in front of them as a gatekeeper. Somewhere around 10% of the web flows through Cloudflare's network. Cloudflare was one of the first companies to provide free SSL encryption for websites. So the connection between your web browser and the website you're going to is fully encrypted and invisible for eavesdroppers to be able to look at.
In short, these folks deal with a lot of encrypted internet traffic, so they need a lot of random numbers. It is possible to write code that will simulate randomness, and that's good enough for a lot of users, but in theory, those numbers could be predicted. They're just being generated by code. So the servers here have to get their randomness from an external and entirely unpredictable source. A lot of home computers treat their own users as sources of randomness. Tiny twitches of mouse movements, the exact milliseconds between keystrokes, or on a phone, maybe even the accelerometer or other sensors. In all those cases, they generally discard the bigger parts, the bits that could just be influenced by humans, and go off to tiny little decimal places, the bits that you couldn't control precisely even if you wanted to. But that sort of human interaction is nowhere near enough for an operation on this scale, hence lava lamps.
We videotape these lava lamps and take the pictures and the video and turn it into a stream of random, unpredictable bytes. And this unpredictable data is what we use to help create the keys that encrypt the traffic that flow through Cloudflare's network. This data is then fed into our data centers and then fed into the Linux kernel, which then uses it to help seed random number generators that are used to generate keys. Every time that you take a picture with a camera, there's going to be some sort of static, some sort of noise. So it's not only just where the bubbles are flowing through the lava lamp, it's sort of the state of the air, the sort of ambient light. Every tiny change impacts the stream of data. A cryptographic hash function is something that we use where even if you have one sort of static image and one little bit changes, it changes the entire stream. So we use that to help scatter the randomness as much as possible. We also collect randomness around the world. So in our London office, we have this thing called a chaotic pendulum. It has 3 pieces, and it's unpredictable in which way they kind of twist and turn together. We videotape that and feed it into our randomness source as well. In our Singapore office, we have a radioactive source that we use to feed into the randomness system as well. So this is not just some stunt that we pulled. It's actually being fed into our real systems.
Whether anything in the world is truly random is arguably a question of philosophy and not science. Maybe everything is just complicated clockwork, but these lava lamps are so chaotic that simulating that camera shot with perfect pixel accuracy, far enough ahead to be useful, while figuring out everything else those images are being put through, it's roughly the same level of difficulty as just brute forcing the encryption in the first place. And even if you could simulate all that, you'd only have one piece of the puzzle. These folks aren't the first to do this. Lava.Round was patented by a company called Silicon Graphics in 1996, but that only lasted a couple of years. Now, of course, there are less flashy and more practical ways to generate random numbers, but then I wouldn't be here. I would be at some other company who'd gone and, I don't know, pointed a camera at a basket of kittens. That'd be a bit higher maintenance, though.
Anyways, I thought that was kind of crazy that lava lamps were used by this giant internet company, and the way that the lava lamp is just a piece of data, and then and again, your data is your input. SHA-256 encryption is just to show you the way this works. Like I've got a number here. And by changing the number, this is what the encryption is. And so changing one number, instead of 1, 2, 3, I'll do 1, 2, 4, changes the entire output. It's the way these encryption methods work is they can take any input, and if one bit on that input changes, the entire hash output changes. And so what they were basically using is pictures of lava lamps, all the lighting, where the lava bulbs were, all of that was the input. And anyways, all this just to say, generating random numbers is computers aren't great at doing it. And so this technique that we're going to do, using this random class to generate a random number is not highly secure, and it's not it's not the best method for generating random numbers. In fact, you'll even see it in your programs. It's like you're supposed to be generating random numbers, but you'll see predictability with this class. And there are less predictable ways to generate random numbers. than the random class. However, this is how we're going to do it in this class. So random class. So we have not this right here is we haven't created an object yet. This is object-oriented programming, and this is really the first time that we've seen how to create an object. So we'll have a syntax similar to this all semester long. Okay, a couple things, you know, we'll break this down as far as random is actually a data type. Like double. My random generator is your identifier. It's just the name of your variable. Assignment operator. Keyword new. When you see the keyword new, you know an object is being created. So an object is being created with the keyword new. Tyler.
You got the N in random.
My random generator. My random generator. Equals new. New's a keyword. It says that there's an object being created, and then we call this method called random. So this is just the syntax for creating a variable that is from a class. The class is the random class. Now to actually get a random number, we have to use my random generator, and we're going to call, as you kind of saw it hinted, whoops. The methods are next int, next. So next is the method that's going to return an int. Again, look at the method signature. I could see that the next method returns an int. So by calling the next method, I'm going to have an int on the left and an int on the right. So I'll say next. And if I type here, I see 3 overloads. It says returns a non-negative random integer. Okay, so if I don't put anything in it, it's a non-negative random integer. So let's just do a console.writeLine random number. Whoops. Okay, so I've created a variable called my random generator. I've used my random generator to generate a random integer, a non-negative integer, stored in an int. Print that out. Let's. All right. 14,867. Let's run this program again. 12,6 something something something. Okay, so that's okay. So we can generate a random number. Yes.
So I know, like, on like the first day, you were saying that you used to play a lot of like MMOs.
I did play a lot of MMOs.
In MMOs, like, they have this kind of randomness, right? Like,
Yeah, the RNG, right? The random number generator.
Is this what they use?
Something like this, yeah.
Okay.
Yeah, this is a random number generator in your turn-based strategies, right?
Mm-hmm.
And in your MMOs. Yeah.
Well, how would you do this if you wanted to simulate like a 20-sided die?
You got a 20-sided die with the values of 1. Now let's look at the overloads. So if I pass it, let's see, a minimum value and a maximum value.
Okay.
So I've got 3. I've got 1, which is just a random number, a random int. I've got a second one that says up to, returns a non-negative random integer that is less than the specified minimum. So let's say less than 21. So this should give me numbers between 1 and 21. So 17, 20, less than 21. So not equal to 21. I should not get 21 here, based on my understanding. Right? So I'm going to get a non-negative number, Sometimes they'll be the same, right? They'll just a couple 2s in a row. See that? But what if I want the numbers between 100 and 200? This is weird. 100, 1 less than 200. Again, read these. Descriptors. Returns a random integer that is within a range. The minimum value is inclusive. The max value is not. So if I say 100, it's 100 inclusive. The max value, the exclusive upper bound. Do you see that? The minimum bound was inclusive, meaning it would include the number. The upper bound is exclusive, so it's basically 1 less than that number.
You mean 1 more?
Well, it should be up to 200. That's how you go 100 through 200. Yeah.
So if you were trying to create like a 6-sided die, it would be like 1, 7?
It would be 1, 7.
Okay.
1, 7. 6-sided die. There's your number 4. Again, number 4. Come on, drag and drop. There's my 2. There's my 3. You would not get a 7. People screw that up all the time because that upper bound is exclusive. So it does not include 7. So it's 1 through 6. There's our lower bound, inclusive lower bound. Okay, that's if you want to generate random whole numbers. Of course, if you want to use, let's see, float random number 2 equals my random generator dot. Look at your methods. Next single returns a float. Next single returns a float. Look at that method header. Okay, so let's type in next single. And there's really, because of this, there's not a bunch of overloads here. And overloads means like there's 3 ways to use this method, or 4 ways to use this method. This one, you notice there's no arrows that I can click up and down, so there's only one version of this method. If you read that, it returns a floating point number greater than greater than or equal to 0.0 and less than 1. So that should get us some sort of number between 0 and 1. All right, you want to play video games? Hey, rock, paper, scissors. 0 represents rock, 1 represents paper, 2 represents scissors. You generate random numbers for the computer. So the user selects paper, the computer generates a random number and picks rock. Who wins? User wins.
So what if you wanted to, I know we were talking about this like last time, but if you wanted to take that decimal from the next single and like round it down to like the 10th place, and 0.5, 0.6.
Math.Round, comma, how many decimals?
Okay.
Now, I think cannot automatically convert. Keep in mind, Math.Round returns a double. So let's go ahead and store this in a double. And that should answer your question, how to basically get 2 decimal points. All right, so using a combination of those 2 things that we learned, we're able to get a random number rounded to 2 decimal points. Good question.
So if there's like a video game, and there's like 6 possible things that could happen, and they're all random, you could like assign each like event to a number, and then have that random number generator generate the number.
Yeah. And then based on the random number generator, now you are walking to the forest instead of walking through the desert, or whatever. Yep.
That's cool.
So we learned a lot today. We got an hour left. Let's go ahead and stop the lecture here.